Hey guys, happy Friday. Sorry I can't be with you today, but I want to talk to you a little bit about some of the things that you saw in the lab that you just completed. Talk to you a little bit about some things that I want to see in your write-up. Keep talking about energy concepts and keep us moving forward. So in the lab that you guys worked on over the last 2 days, you were changing some aspect of a system where we had our mass. Let's see, let's get this, good. We had our carts, and we had our spring, and we were stretching the spring and looking at the velocity of the cart as it got pulled along. At its core, what you were looking at is the transfer of potential energy in the spring, which we symbolize with US, into kinetic energy in the cart. And so we stretched the spring some amount, which if you remember from our equations, we said that the elastic energy or the potential energy in the spring is equal to 1/2 k x squared. And actually, let's change that just a touch, and let's say delta x squared, because as we recall, we're really looking at the change in stretch length, not the absolute length of our spring. And this is being converted into kinetic energy of the cart, and we know that kinetic energy of the cart is equal to 1/2 mv squared. So hopefully you created your graphs today, and depending on what variable you change, what your independent variable was, you're going to get some different types of relationships. But for all of us, our velocity should have been our dependent variable, and then either mass, let's do mass, k value, or stretch distance. Those were our three independent variables. So IV. And of course, whichever one you were changing, the others should have stayed the same. Now, one of the principles that we were relying on here, even though we hadn't specifically stated it, is the principle of conservation of energy. And we said in our previous discussion on momentum, when we had conservation of momentum, it was dependent on our system being open or closed. And we're going to talk about our systems in the same way when we talk about energy. The conservation of energy simply says that in a closed system, the total energy of the system does not change. And again, our difference between closed and open systems has to do with external versus internal forces. If there are no external forces acting on the system, then it's a closed system. If we have external forces acting on the system, then it is not a closed system. So let's look at our spring and cart system a little bit more closely. So we had our cart, we had our string, we had our spring, and we had our hand. And actually, you know what? Let's stretch our spring. So we had it stretched out here. And then we had our track. And the forces involved here, let's look at our cart. So for our cart, we had Fg, we had Fn, we had Fs, and a little bit of frictional force. Okay, on our spring, oh, that's interesting. We have the force of the cart on the spring, which is, of course, third law pairs here. And then we had the force of the hand supporting it. Now, within our system, and actually, this was just more or less holding it to support it. Looking at this then, our important forces are these two right here. If our system, in this case, is the cart and the spring, then our two important forces are the elastic force and or the force of the spring on the cart and the force of the cart on the spring, which are both internal. The normal force and the gravitational force balance each other out on our cart, so we're not too worried about those. But we do have this little force of friction over here. So in this situation, if we were to say, well, let's ignore friction, then we would have a closed system. We're taking real measurements, working with real data, though, and so we know that there is this external force of friction acting on the system. And so that external force is going to cause it to be an open system. So what that means is that the total energy I, we'll call it total energy initial, is going to be greater than the total energy F. And this is of our system. Of our system, which in this case is the cart and spring. Now, one thing I'm going to ask you to do as you analyze your data is to not just look at the relationship between your independent and dependent variable, but also compare your initial and final energy, because we want to see how significant is that force of friction. How much energy is it really taking out of our system? And so we're going to then, if we look at the initial state of our system is where we have the spring held, you've pulled back the cart, and so now we have the stretch spring and the cart not moving. So within our system, we have our total energy is the kinetic energy plus the potential energy. And this is initial. And then our final should, theoretically, without friction, equal the same, Ke plus Us. Final. Initially, our kinetic energy is 0 because the cart isn't moving. In the final state, our potential energy should be 0 because the spring will have fully unstretched. So what this means, if we rewrite this, is that the initial potential, USI, is equal to the final kinetic, or 1/2 K delta X squared is equal to 1/2 mv squared, where the delta X is your stretch and then V is your final velocity of the cart. So as part of your analysis, I would like you to compare these two as a percent. So what is the percent difference between the initial and the final, or between the initial energy and the final energy, because we know it should be a little bit less because you have friction acting on it to pull energy away. Now, whether we're talking about within our system or outside of our system, what we should see is that we have energy being converted from one form to another. And even in our friction, that energy isn't really being lost. It's just being taken from our system. So in this system, we have elastic energy being converted into kinetic. But if we think about friction, friction is actually also converting energy. But it's taking that potential elastic, that kinetic energy, and it's converting some of our kinetic into thermal energy. Or as we used our symbol, delta E therm. So at a very, very small scale, the energy of the molecules in the track and in the wheels was increasing. So the temperature in the wheels, or the temperature of the wheels and of the track was increasing, although of course it was so small that we wouldn't be able to measure it. So we're not really losing energy, just like when we talked about momentum, we're not really losing momentum. It's just leaving our system. And so the total energy of our system, which in our case is our spring and our cart, is decreasing because that energy is going out. Now, the mechanism for that change in energy is force. And so in the case of converting the elastic energy to kinetic, so US to KE, the conversion is happening because of the elastic force on the cart. So the spring is exerting a force on the cart as it unstretches, causing it to speed up. The conversion of kinetic energy to thermal, so KE to delta E therm, is caused by the force of friction on the cart. Okay? So both of these energy conversions are caused by some force acting on some object within the system. And this then leads us to another concept that we call work. And work, in the physics sense, is equal to, let's actually write it out, work is equal to FD, force times distance. And specifically, distance traveled in the direction, that's a D, wow, that is awful, I'm sorry, direction of the force. So our spring does or exerts a force on the cart along the path of the track. The cart moves in that same direction, and so we're increasing the kinetic energy of the cart as the elastic energy of the spring decreases. So we have some force, elastic force, as the cart moves some distance. This is equal to the work done by the spring. What we should notice also then is that work is causing a change in kinetic energy, and what we find that work is equal to the change in energy of a system. So not only is the work that the spring does on the cart equal to force times distance, it's also equal to the change in kinetic energy of the cart. So work is equal to delta KE in this case. So work of the spring is equal to delta KE. Now, with our spring, what we need to keep in mind is that it is not a constant force, right? It is an increasing force as the spring gets stretched greater distances. So our graph is going to look like this. As we've done with a number of these, and as we did that very first day, what we find is that it's the area under this graph that is important. The area under this graph gives us the work done on the cart because it is F times X. So if we look at that, the area is equal to, well, here we have a triangle, so it's 1/2 base times height. So we'll say 1/2 F times delta X. We said previously that F is equal to negative KX, negative delta KX, or delta X rather. Let's not worry too much about the negative because that just tells us that the direction of the force is opposite the direction of the displacement or of the stretch. So we can say A equals 1/2 K delta X times delta X, which is equal to 1/2 K delta X squared, which is our elastic energy equation. So for the case of our spring, the work done on the cart is equal to the energy stored in the spring. And this takes us back to our conservation of energy. However much we stretch that spring, we're increasing the amount of energy that's stored in the spring. We attach it to the cart, we let the spring pull the cart. All of the energy, theoretically, that's stored in the spring is getting converted to kinetic energy in the cart, and it's being done through the force of the spring on the cart. Now, we have our cart that's moving along at some velocity because the spring is pulling on it or has pulled it. But at the same time, we have this little force of friction acting in the opposite direction. That force is acting along that whole distance that car is traveling. We know that work is equal to force times distance. In this case, the force is opposite the direction of the cart movement. So the force is to the left if the cart is moving to the right, because friction is always opposite the direction of motion. And so what this means is that we have negative work being done on the system. And while work and energy are scalar, work and energy are scalar, you can have positive and negative work. In this case, it's more kind of what we typically think of in regards to positive and negative. So that's not a dash, that's a negative. Negative work's being done in the system, which means that energy is being removed from the system, which again in this case is our cart and spring, which is why our final kinetic energy is going to be less than our initial elastic by some amount of value. Because work is equal to the change in energy, The units are going to be the same, and those units for both work and energy are joules. Okay. Quick discussion of our joules. We say KE is equal to 1/2 mV squared. Our units here are kilograms times meters per second times meters per second. That gives us kilograms times meters squared per second squared. This is the joule. Just like a Newton is a kilogram times meters per second squared, a joule, symbolized with a capital J, is kilograms times meters squared per second squared. Okay, but what about our US, which is 1/2 K delta X squared? K, if we recall, our spring constant is newtons over meters. So our units here are kilograms times meters per second squared over meters times meters because it's x squared. So these meters cancel out. We're left with kilograms times meters squared per second squared. Look at one other one, gravitational potential energy, which is mg, and actually this is change in gravitational potential energy, is mg delta h. So m is kilograms. Our g is newtons per meter, or meters per second squared. Our change in height is measured in meters. So again, we can see that we have, once again, the exact same units. The other thing to notice with our gravitational potential energy is that mg is the force of gravity, so this very quickly simplifies into Fg times delta H, which for a falling object is the work done by gravity. So the change in potential energy is equal to the change in kinetic energy as the object is falling, changing that gravitational potential to kinetic. So hopefully that's enough to help you do a little bit more analysis in your elastic energy, kinetic energy lab, your spring lab that we just completed. I would like you to have that final write-up done by Tuesday. You can save it as a PDF, so it's in a Google Doc. I want you to save it as a PDF and then upload it to the assignment in Schoology. Now, the second part of this, we're going to continue on talking about energy and diagramming energy. And I want you to take a look at this Khan Academy video. It's going to tie into your packet to the work that you're going to be doing on pages 13, 14, 15, and 16. Diagramming energy flow, showing this idea of conservation of energy, open systems, closed systems, and work done on systems. So you're going to take a look at this video, and then when you're done, work on the practice problems that are in your packet.
I want to talk to you about lull diagrams. That's right, I said lull diagrams. These are a great way to visualize conservation of energy, and even better, they force you to think about what's part of your energy system and what isn't part of your energy system. And if you don't know what an energy system is, maybe that's where we should start. An energy system is an object or a collection of objects whose energies we're going to keep track of, and we're going to keep track of them in these two charts. And notice, it looks like an L, and then an O, and then an L. That's where they get their name from. This isn't laugh out loud. This is an energy chart, a circle where we're going to define our system, and then another chart. So to understand what these lull diagrams mean, let's just look at an actual example. let's say you took a mass M and you released it from rest from a height h, and this mass falls down. The first thing we should do is choose what is going to be part of our energy system. Whose energies are we going to keep track of, and whose are we not going to keep track of? The way people typically do this problem when they're doing conservation of energy, they would say it starts with potential energy, and then it turns into kinetic energy. And if you're doing that, what you're really doing is you're saying, I'm taking my mass, that's going to be part of my system. So I'm going to take this mass here, I'm going to make that part of my system. So we'll keep track of the energy of this mass. And then if you're talking about gravitational potential energy, here's the weird thing. You're also talking about the Earth. That Earth is part of your system. So this is the Earth right here. It's got continents, and it's got California and Mexico and South America, and there's Florida, and there's all kinds of stuff here. So now that we've selected our system, we can go ahead and start charting what the energies look like. So what kind of energy was there initially in this system? There was gravitational potential energy because this mass M started a height h above the Earth. So I'm going to represent that with this bar. This is going to be a bar chart. I'm going to just go up 4 units. I'm going to say there were 4 units of gravitational potential energy. You might be like, how do you know there were 4? How do you know there weren't like 3 or 5 or 4.2? Well, it doesn't really matter too much. The real value in this lull diagram is being able to conceptualize what's happening to the energies. No matter what you draw over here, you just want to be consistent when you then draw this diagram over here, and I'll show you what that means in a minute. So for now, let's just say there were 4 units of gravitational potential energy to start with. Was there any kinetic energy? Nope, because it was released from rest. So if we drop this mass, it starts with no kinetic energy. And this US here is going to be any spring energy. We won't have that for this example, because there aren't any springs, so there won't be any spring or elastic energy. So that's it. We just had gravitational potential energy to start. And then what did that energy turn into? If this was the initial position, what kind of energy do we have when the mass gets right above the surface of the Earth, right before it's going to hit the Earth? What kind of energy is there? There's going to be kinetic energy. So this mass is going to have kinetic energy. And we know it's going to have kinetic energy because it's going to be moving right before it hits the Earth. And kinetic energy is the energy an object has because of its motion. So it's going to have kinetic energy. How much kinetic energy is it going to have? Well, energy is going to be conserved in our system, and since the energy is going to be conserved, if I started with 4 units of gravitational potential energy, I should end with 4 units of kinetic energy. Now you might be confused, you might wonder, why wasn't there any gravitational potential energy? Well, I was assuming that this ground was the h equals 0 line, and we know that the gravitational potential energy is mgh. Where h equals 0, the potential energy is 0. So when this mass gets down to the final point, which I'm representing in this diagram, it no longer has any potential energy since the h would be 0. And since it has no potential energy, all of this gravitational potential energy it had initially has to turn into kinetic energy in order for the energy of our system to be conserved. Now if I were you, I might object and say, wait a minute, we learned earlier that when work is done, energy gets transferred and the total energy of an object might change. And this Earth is pulling down on this mass, right? So the Earth is exerting a gravitational force downward. The object's moving downward through some displacement. That means the Earth's doing some positive amount of work on this mass, giving it energy. Doesn't that mean the energy of the system is going to change? And the answer is no. And the reason is this Earth is also part of our energy system. So the Earth did do work on the mass, and this mass gained kinetic energy, but since the Earth and the mass were both part of the system, this work was internal to the system, and internal work never changes the total energy of the system. And if that was confusing, think about it this way. Let's say you and your friend, instead of the Earth and the mass, there's you and your friend. And instead of energy, we'll talk about money. You, the Earth, give your friend, the mass, $10. Instead of 10 joules of energy, you give him $10. I ask you, how much total energy is there between you and your friend? Well, there's still the total amount. You lost $10, your friend gained $10, but between the two of you, you still have the total amount of money you had when you started. And the same is true with energy. Whenever work is done internally between objects in your system, there's no change in the total energy from one chart to another. That's why I had to draw the kinetic energy as 4 units, because no energy entered or exited our system. And something that's really useful about these lull diagrams is that you can translate them straight into a conservation of energy equation, because whatever initial energy that you start with, plus any external work that's done, has to equal the final energy that you end with. And the reason is, external work is how much energy gets transferred into the system, So if you start with 10 joules of energy and you transfer 5 joules of energy into the system, you've got to end with 15 joules of energy. So we can just plug straight into this. What did we have for our particular scenario? We started with potential energy, so our initial energy was mgh plus external work. There was no external work. There was only internal work, so this would be 0. And that's got to equal the final energy. The only type of energy we had to end with was kinetic energy, 1/2 mv squared. And then if we had numbers, we can plug into this formula and just solve for the height or the speed or whatever we wanted to solve for. So what would an example look like where energy wasn't conserved? In other words, where there was external work done on the system? Well, we could use this same example. I just need to take the Earth and I'm going to stick this Earth outside of our system. So now our system is just the mass m. What that means is that the work done by the Earth on the mass is now going to be external work. And since there's external work done on this system, the system's energy has got to change now. It's not going to stay the same. You're not going to see the energy of this system remain conserved since something's giving it energy. The Earth is giving this mass energy this time because it's doing external work. So how would that change our lull diagram? This mass m still ends with kinetic energy. I mean, just by imagining the Earth as not part of the system, that doesn't change what actually happened. The mass still has to get down here with 4 units of kinetic energy. It's still moving just as fast as it did before, but our system, which is this mass, has to be gaining energy. And the way that's possible is that the mass does not start with any gravitational potential energy. So people don't like this. People are like, wait, what? Of course this mass starts with gravitational potential energy. It started up here, but technically speaking, gravitational potential energy is an energy that exists between two masses. It takes 2 to tango, and it takes 2 masses to have gravitational potential energy. If I stick one of these masses out here, it can do work on the other mass. We wouldn't say that it started with any gravitational potential energy, so this would now be 0, but we would say that there was external work done. So that's where this energy comes from. The Earth is now doing how much work? Well, if the mass gained 4 units of kinetic energy, then the work done had to be 4 units of work. So if you stick the Earth outside of the system no longer has gravitational potential energy. The Earth is doing external work on the mass. And this might bother you. You might be like, wait, but it's the same situation that's happening. All we did was change whether we considered the Earth part of our system. So how can that change the math? It didn't really. I mean, if you think about it, instead of the 4 units of energy existing initially as this potential energy and having no work, we're just saying that there was no potential energy to start, and there were 4 units of external work done. It's just a different story. The numbers will come out the same, and it's all going to be consistent, but depending on whether you stick that Earth outside of your system or inside of your system will determine whether you say that there was initially gravitational potential energy, or whether you say there was external work done on the mass. So let's look at another example. Let me get rid of this. Let's instead consider this example where a mass starts compressed against the spring from rest. That'll be our initial point. And it fires the mass, and the mass goes up this incline and comes over here. And then it's moving with some velocity over here. We'll make this our final point. So if we want to make a lull diagram, we first have to pick what's part of our energy system. Because if we don't know what's part of our system, we don't even know what's going to be eligible to have an energy in here. So again, let's make the mass part of our system. So the mass will be part of our system. Let's make the spring part of our system. So we'll put the spring in here. And let's again put the Earth into our system. So what would this lull diagram look like for this scenario? Well, since we start from rest, we don't start with any kinetic energy. And even though the Earth is part of our system, which means our system could have gravitational potential energy, I'm just going to assume that the mass starts at h equals 0. So let's make the ground h equals 0. That way, this potential energy term, mgh, starts as 0, so there'd be no gravitational potential energy to start with, and the only energy we would start with is the fact that this spring is coiled up, ready to explode and fire this mass forward. All this energy is stored up as spring or elastic energy, so we will have elastic or spring energy to start with. Let's just say we started with 5 units of spring energy. Again, this is somewhat random. For a particular problem with numbers, you could solve for exactly how much spring energy you started with, because remember, spring energy can be found using the formula 1/2 kx², where x is the compression of the spring and k is the spring constant. But to keep things simple, let's just say we start with 5 units of spring energy. So what would our final energies look like? If this mass is up here moving, if it's moving, we know it's got kinetic energy. So I can say there's kinetic energy. How much? Again, to figure out exactly how much, you'd have to solve for your particular problem and know this height. But to give you an idea of what conservation of energy says, let's just say there were 3 units of kinetic energy that you ended with up there. What other kinds of energy do you have up here? Well, you're going to have gravitational potential energy because this mass starts above the h=0 line. So since the mass is higher up in the air, it's got gravitational potential energy. So now, if I say there's 3 units of kinetic energy and I started with 5 units of spring energy, if energy is conserved, I better end up with 2 units of gravitational potential energy. So I could draw 2 units, and now I'd make sure that if I started with 5 units of energy, I've ended with a total amount of 5 units. That would say energy is conserved. Let's check. Is energy of our system going to be conserved? We can determine that by just figuring out whether there were any external sources of work. Did anything external to our system do any work? If not, the total energy's got to stay the same. This 5 units has got to turn into 5 units over here. And if we assume that these surfaces here are frictionless and that there was no air resistance or no loss in energy due to dissipative forces, there will be no external work done because everything's part of our system. So like work was done in here, the spring did work on the mass, giving it energy. There was internal work done, but since there was no external work, the energy had to be conserved. We can write this in the equation again by saying that the total energy we start with, the spring energy, which would be 1/2 kx² plus any external work done, but the external work done was 0 since everything is internal, has to equal the final energy, and the final energy here is the kinetic energy, which is 1/2 mv² plus the potential energy, which is going to be plus mgh. And now if you had numbers for a particular problem, you could just plug those into here and solve for whatever variable you were looking for. But you might be wondering, what if there is friction between the mass and the ramp? What if there is friction over here? What would that do? Well, there's 2 ways we can handle it now. You know there's 2 ways. We can include these surfaces as part of our system, or we could say that those surfaces are outside of our system. If the surfaces are outside of our system, we would represent that as them taking energy away. Now there's external work done, but instead of the external work giving our system energy, the external work is taking energy away. This friction is taking energy and turning it into thermal energy. That's what this extra spot is here, for thermal energy. But since the surfaces are now not part of our system, we wouldn't show that over here. We would just include that as part of the external work done. So there would be some negative amount of work done. Maybe the surfaces did -1 unit of external work. What that would mean is that if we started with 5 units of energy and there was -1 unit of external work done, we've got to only end up with 4 units of energy. But my potential energy's got to be the same. I mean, I ended up this high, so that can't really change. So that means my kinetic energy is now going to be smaller, and that makes sense. The friction slowed this mass down. I ended with 4 units of energy, even though I started with 5, because there was -1 unit of external work done by the friction on these surfaces. That's one way to handle this problem, and that's all consistent. The other way to do it, we could just say that our surfaces, which we said were external, are now internal to our system. That way this external work done is no longer external. This work done is now going to be internal. The surface took the energy, it still did negative work, but since it's inside of our system, that's now going to be part of our energy system. So how would we represent that? It would no longer be a -1 here. We wouldn't say that this is done. We'd essentially, conceptually, move that -1 over by adding 1 to both sides, and that means we would gain some thermal energy. I'm going to write that as delta E thermal, because there's going to be some gain in the thermal energy of our system. And I would represent that now not as an external work done, but as 1 unit of thermal energy generated during this process. So recapping, lull diagrams are a great way to visualize what we're talking about when we say conservation of energy, and since we define our system, they're a nice way to visualize what we mean when we say that the total initial energy of our system plus any external work done on our system has to equal the total final energy of our system.
Okay, so what I want you to do now is go ahead and go to your packets. Page 13, you're going to see the first set of energy flow diagrams. start working through them with your team. Try and get through as many as you can. You should be able to actually get through them all today. And then I've got another really short video just walking through the first couple of them so you can see how they should look. And then the key for these is in Schoology. Other than that, have a good weekend, and I will see you on Tuesday. If you have any questions, shoot me an email.